All right, everybody, today we're going to talk about section 4.12. That deals with the law of sines. So we've seen before in sections 4.10 and 4.11 how to solve right triangles, that is, find the sides and angles of a right triangle, given some information. With this lecture, we're going to be looking at how to do that for a non-right triangle. So say we have, consider the triangle, this guy here. Let's label the side, the angles, the vertices. Let's say that's A, B, C. Okay. So the vertices are A, B, and C. Let's say this angle up here is alpha. This angle right here is beta. And this one is gamma. Okay. And then we have our sides here. So normally we will label them as lowercase letters. So this is lowercase c, lowercase b, lowercase a. Okay? So this is a non-right triangle. You can see we don't have any right angles in it. So what we're going to try to do is develop a way to find the sides and angles of this non-right triangle. Okay? One of the ways that we do that is called the law of sines. So here's our theorem. Law of sines says that the sine of alpha over A is equal to the sine of beta over little b equals the sine of gamma over little c. Okay? So basically it's the sine of this angle divided by the side across from it is equivalent to the sine of the other angles divided by the sine across from those. Okay? So here I want to do a quick proof of what the law of sines, how we get the law of sines. Okay? So if we consider this triangle up here, let's do a little proof. Okay? What we can do is consider the height of this triangle. So what I can do is draw a line from vertex A down to its side. Do that in a dotted line here, so that it is perpendicular to this bottom side. So here we have a right angle. Okay? And let's call this distance h for height. Okay? Now, what we notice is that there are two right triangles that we have now inside of our triangle. So we have this right triangle here. Right, we have this right triangle here. And then we have the smaller right triangle on the right-hand side here. Okay? So based on what we know from the last couple of sections, is that we know that the sine of beta, right, the sine of this angle here, if we're just dealing with this triangle, right triangle, the sine of beta equals opposite over hypotenuse, so that would be equal to h over c. Okay? And if we focus our attention on the smaller right triangle, we know that the sine of gamma, this angle, the sine of gamma, is equal to opposite over hypotenuse here. So the sine of gamma is equal to opposite h over the hypotenuse, which would be b here. Okay? Now, because h is the same in both cases, if we solve for that, then those two quantities will be equal. So if I solve this for h, all I need to do is multiply by c on both sides. So I'm going to multiply this side by c. Multiply this side by c. So we'll get c times the sine of beta is equal to h. I'm going to do the same thing here, but we'll multiply by b. Multiply by b on both sides. So b sine gamma is equal to h. those b's will cancel. Okay? So because these h's are the same, they're coming from the same triangle, then what we can do is set these two left-hand sides equal to each other. So this implies that c sine beta must be equal to b sine gamma. They're both equivalent to h. And if we do a little bit of algebra, I'm going to divide both sides. I'm going to divide this side by c, both sides by c, and divide by b. We can get an equivalent form. So the sine of beta divided by b equals the sine of gamma divided by little c. Okay? So that gives us one of the equalities here. If I were to do this same process, but maybe label the side, maybe label these vertices a little differently, we would get exactly this relationship here. Okay? So that's where the sine, law of sines comes from. So all we would need to do is just, if we know some information about this triangle, we would just have to solve these little equations here. Okay? So let's look at an example. Now, various information can be given for our problem. So let's look at a first example here. Example, let's say that we're given two angles. Given two angles and one side. Or the angle side type of problem. Angle side. All right. So let's do one here. Let's say that gamma is 102 degrees. Beta is 28 degrees. And little b is 27.4. Okay? So we know two of the angles and one of the sides. So let's draw a little picture of that and see what we get. So here, all right, so we can put beta over here, so b. So beta is 28 degrees, that looks about like a 28-degree angle. And gamma is 102, so let's make the obtuse angle equal to gamma. So let's say that's C, big C. Let's call this A. So 102 here. And little b is 27.4. So where would little b be at on this diagram would be across from big B. So there's little b there, which is 27.4. Okay. So our mission here is to figure out all the other missing parts of this triangle. So we need little c, little a, and alpha. And those are the missing pieces here. Okay. So first things first, we can actually find little alpha pretty simply, right? Little alpha can be generated from that relationship between the angles of the triangle. Recall that the three angles of a triangle must add up to 180 degrees, right? So we know that alpha plus 28 plus 102 must equal 180 degrees. So let's solve this for alpha. Alpha plus these two combined would give us 130. So subtracting 130 from both sides gives alpha equal to 50 degrees. Okay? So alpha is 50 degrees. I'll just write them in there as I find them. Okay? All right, now we need to find the sides, right? So in the right triangle unit, what we would do is just set up either a sine, cosine, or tangent ratio to get the missing sides. But this is not a right triangle, so we can't really do that in the same way. So what we need to do is use our law of sines, okay? In order to use the law of sines, we need to have a angle and side combination. So in this case, we have angle beta, which is 28, and the opposite side, which is 27.4 here. So because we have that, and we know that the sine of beta over b equals the sine of alpha over a equals the sine of gamma over c, this is our law of sines, what we can do is just pick out some ratios and solve them. Okay? So we know this guy here. So first, to find little a, we know that the sine of beta over b equals the sine of alpha over a. So we know beta is 28. We know b is 27.4. We know alpha to be 50. And we're looking for little a. So we have all of our unknowns solved for except for little a. So I'm just going to work with this ratio for now and use the law of sines. So the sine of beta, which would be 28, over little b is 27.4, equals the sine of alpha, or sine of 50, over little a. I'm going to disregard this for now because we don't really need him. We can only solve this one equation at a time. We'll come back and use this in a minute to get little c. Okay? All right, so all we need to do is just solve this. So let's find our sine of 28 and sine of... so in order to solve this proportion here, what we can do is just cross multiply. So I'm going to cross multiply these two values here and set up a new equality. So the sine of 28 times a is just a sine 28 equals 27.4 times the sine of 50. 27.4 times the sine of 50. Okay? So let's go ahead and find out what these values are. What is the sine of 28? So make sure your calculator is in degree mode. And let's get that. Sine of 28 is 0.4695. So this is 0.4695a equals this guy over here, 27.4 times sine 50. This is 20.9896. I like to use 4 decimal places because it avoids any rounding errors that you might encounter. So now to find a, just divide both sides by this decimal here. Okay. So doing that gives a equal to approximately 44.7. So we can round our sides to 1 or 2 decimal places depending on what the problem is. So 44.7 is our a. So I'm going to go back up to a, write that in there. 44.7. This is the side length, so we don't put any degrees on it. Okay? Alright, and that's it. That's how we find a. Now to find c, we can do the same kind of thing. And we can use either of the 2 ratios to equate to c here. So we can use sine of 28 over 27.4 equals whatever. Or we could use our new value since we know the alpha and a combination now. So it doesn't matter which one you use. So to find little c, let's just use our b ratio again. So sine of 28 over b, which is 27.4, equals, now we're going for sine of gamma. Gamma is 102, sine of 102 over little c. Sorry about that. So again, sine of 28 over 27.4 equals sine of 102 over c. And we do the same process. So cross multiply gives us c times this sine of 28 equals 27.4 times the sine of 102. So again, we'll have 0.4695 c equals 0.4695 26.8012. And dividing both sides by this value here. Gives us little c is 57.1. Okay. So little c is 57.1. Okay. And all of these values make sense, right? Because the biggest side should always be across from the biggest angle here. So 102 is here. The 57.1 is the largest side. The smallest angle is 28. It's across from the smallest side, 27.4. Okay? So you can see that the law of sines is pretty simple. Now with this problem, with the angle-angle-side type problems, there's only one triangle that can be made. If we know two of the angles have to be 28 and 102, and the other one has to be equal to 50. There's no other triangle that has two angles that are 28 and 102 that has a different angle here because of this rule. Okay? Now, in subsequent problems, if two sides are given, that means that we could possibly have two different triangles. All right, so let's take a look at that. All right, so this is the ambiguous case. That's the side-side angle case. Okay? So if we know only one of the angles, then we have options for the other two. And it's dependent upon these sides. There's three outcomes for this. One, there could be no solution, or slash triangle. There could be just one triangle. Or it's possible that the side and angle makeup could produce two triangles. So the no triangle case, one triangle case, or two triangle case. Okay, so what am I dealing with here? So for the one triangle case, it's possible that we have given angle here. Let's say we have this angle here, and we have these two sides. It's possible that the third side could be too short. Okay, could be too short when we find it. The second given side could be too short to even connect to this line down here, right? So no triangle can be formed. All right. The second case is with a one triangle solution. So if we have that same angle there, if this line is long, this other side over here is, so we know this side, we know this side. If this triangle is long, there's only one possible triangle, like we have to swing that side here to connect, right? So if this second known side is longer than the first one, then there would be only one triangle that can be formed. Okay? Only one triangle can be formed. And then there's the case where the side is shorter but not too short. Okay? So we know this angle here. It's possible that we could form a triangle, let's say, like this, where this side is known. But if we were to rotate that side, it's possible that we might get a smaller triangle over here with the same side makeup. Say this guy here and this guy here are the same. So we could get this bigger triangle overall, or we could get this smaller kind of sliver of an oblique triangle over here, where this is the same value as that. Okay? So we could have two triangles can be formed. So we always want to test, here, this side length here and this side length here. It's possible that we could create two triangles, one big overall triangle here, or one smaller triangle there. Okay? So we always want to check that. So let's look at an example. All right, so let's look at the side-side angle case. So when two sides are given and one angle is given, we always need to check to see whether there is one triangle, no triangles, or two triangles. So we'll go through that. Let's look first at the one triangle case. Okay. So let's say that we are given A is 22, little a is 22, little b is 12, and alpha is 42 degrees. Okay. So let me draw my triangle over here. All right. All right, so I'm going to always put the known angle here. So let's say that that's A, 42 degrees here. Okay. And little a is 22. And let's say B is right here. B is 12, so C is the unknown. Everything's unknown about C. Okay? All right, so what we're going to do first is find angle beta here, right? So here's beta, this angle right here. Okay? So we can do that by just using one round of Law of Sines. One round of Law of Sines because I have an angle and side combination. All right, so let's do that first. So we know that the sine of alpha, 42, over little a, which is 22, must equal the sine of beta over 12. Okay? So let's solve this. So let's cross multiply. 12 times sine 42 equals 22 sine beta. Okay? All right, so let's calculate that. 12 times the sine of 42 is 8.0296 equals, now we can't multiply these because we don't know the angle, so we'll just leave that as 22 sine beta. So solving for beta, I can divide by 22 on both sides. Let's do that, divide by 22. That gives us 0.36498 equal to the sine of beta. I'm going to give myself a little space right there. All right, so we haven't really dealt with how do we get this, how do we get rid of this sine? Well, note that this is not like the sine times beta, it's like the sine of beta. So it's a different operation all into itself. So we can't just divide by sine, right? We have to divide by some number, and sine is not a number. So if you notice on your calculator, if you look at the sine key on any scientific calculator, normally what you'll see is right above that is this other little sign to the -1. This is called the sine inverse. So it's like the opposite of sine. It's like the, if sine were multiplication, sine inverse would be division. So there, or if sine was addition, sine inverse would be subtraction. It's the opposite operation for it. And what it does is, if sine is an acute angle, it cancels out the sine. So that's what we're going to do to both sides. So here's how we're going to do it. We're going to take the sine inverse of both sides. I'm going to write that here. Sine inverse of the left side, sine inverse of the right side. The reason why we do this is because sine inverse cancels out sine. So these, you can consider these as like cancellation right here. Okay? So on the right-hand side, beta pops out. And what we need to do is calculate what the sine inverse is. So access that sine inverse button, and then just type in that number, 0.36498. Gives us 21.4. So let's go to one decimal place. 21.4 degrees is beta. Okay? So that's what we have here, 21.4. All right. So what would gamma be? Well, gamma would be easy to find now because this is 42, this is 21.4, so this has to be the difference from 180, right? So let's find that pretty quickly. So gamma would be 180, take away the sum of the other two. Or 116.6 degrees. So this big angle up here is 116.6 degrees. All right. Now let's do the analysis for the second triangle. Right? So the second triangle, if you recall from the previous piece of this lecture, is basically what we're going to do is take this A value here and try to see if we can't swing it over this direction to create a smaller kind of sliver of a triangle on the left side. So basically what's going to happen is, let's say we take this side, swing it over. So this would also be A. A equals 22. Okay? So the point B would shift over to here. That would be our new B. If it's possible. Okay? So what we need to do is analyze to see whether the angle combination that we have for A and B will work for this triangle here, because we would have another angle for alpha. So if we disregard this triangle, alpha would then be up here, right? Or excuse me, not alpha, but gamma. Gamma would be up here in this triangle. Okay? So let's see if it's going to work. Do we have enough room for another angle gamma to exist up here? Well, here's how we do it. Well, notice in this triangle, this is an isosceles triangle. It has the same sides, 22 here, 22 there. If these are the same size, then we know that the angles across must also be the same size. So this angle would be 21.4 also, same as this, right? 21.4. That means that this larger angle next door to it, since it's sitting on a straight line, has to be supplementary to this guy. So this would be 180 take away 21.4, which gives 158.6 degrees. So this would be 158.6 degrees. Okay. Now if we focus on the smaller triangle, do we have enough room using that 180 degree rule to get another angle right here? Well, if we add 42 plus 158.6, that is larger than 180. So there would be no other angle that could exist in this second triangle. So based on that analysis, this implies that only one triangle exists with this given information. In fact, if the first angle you find is smaller than the given angle from the problem, so let's make a note. If the angle we find is smaller than the given angle, only one triangle exists. Okay? If it's larger, we'll see that two triangles can exist. We'll get to that in a minute. Okay? So all we need to do is figure out, so we know two sides already, and we know three of the angles. So all that's left to do is just to find this bottom side C here. So we're just going to do one more round of Law of Sines to get that. So lastly, sine of 42 over 22 equals the sine of the C angle, or gamma, which was 116.6 over little c. Okay? So again, we know A, we know little b, we know alpha, we know beta, we know gamma. So all that's left is the other side, little c. So let's do our cross multiplication. So c times the sine of 42 equals 22 times the sine of 116.6. Sine of 42, so we'll get 0.6691 C equals 19.6714. Divide both sides by 0.6691, gives us C. So it looks like 29.4. Okay. So here is all of our missing info. So again, you may not have to go through all of this geometric analysis. If you notice that the angle that we get on that first law of sines is smaller than the one that we're given. Okay? Let's do the no triangle case. So for the no triangle case, that means that the side makeup is just out of whack, so we can't generate a new any triangle at all. So let's say A is 15, B is 25, and alpha is 85. Okay? So if we were to draw that, always put your given angle here. So that would be alpha is 85 degrees. Known value here, B down here, C up here, and 25 for B, little b, and 15 for little a. Okay. So let's look to see what happens when there's a no triangle case. So let's do a law of sines to figure out what beta is. What is beta? So you know the sine of alpha, 85, over little a is 15, equals sine beta over little b, 25. All right. Cross multiply, we'll get 25 sine 85 equals 15 sine beta. And divide both sides by 15. So the sine of beta will equal this product here. We can put it all in the calculator at once. 25 sine 85 divided by 15. That gives us 1.6603. 0.6603. Okay. Now to extract beta, so remember to cancel off that sine, you have to use sine inverse. So let's take the sine inverse. Sine inverse. And see what happens. So here, these will cancel. So beta equals, let's put in our sine inverse of 1.6603. Oh, we get an error message. So when this happens, there is no triangle exists, right? This the side makeup, this A side is just too short to connect to the other part. Now, why is that? Well, if we go back here, note that we had the sine of beta is 1.6603. Now remember from our graphing unit, the sine function can only be numbers in between, can only produce numbers in between 1 and -1, right? This number is outside that range. So we're never going to get, remember their sine function looks like this, right? That's 1. We're looking for some angle where it's 1.6, and that is never going to happen, right? So this is the no triangle case. So we're done with that problem. So if you get an error from your calculator when you do that first law of sines, then there's no solution, okay? No triangle exists. All right, let's do the two solution case. Two triangle case. Again, all of this ambiguous case comes from when we know two sides and an angle. All right. So let's say A is 12, B is 31, and alpha is 20.5 degrees. All right, so let's draw that. All right, so the known angle is alpha. Let's put him here. It's A. And then our other side given is B, so let's put him over here. Little a is 12, and little b is 31. So let's say that's C. Here's beta. Okay. All right, so let's go for our beta first. Sine of 20.5 over 12 equals sine beta over 31. Cross multiply. So 31 sine 20.5 equals 12 sine beta. And divide by 12. So sine beta will equal 0.9047. Taking the sine inverse. Is beta equal to 64.8 degrees. So note that beta is now larger than the angle that's given. This is an indication that there are two solutions. This implies two triangles exist because this angle is bigger than the given angle. Okay. So 64.8 degrees here. So we can find our first one here, right? So the reason why this two triangles can exist, because if we think about swinging A over this way, this would also be 12. That means that this angle right here is 64.8. So this angle, or another B, say this is B1, this is B2. Our second beta would be equal to 180 take away 64.8, which is 115.2. Okay. So you can see when we add these two together, there's still room for the 180. So there's still room for this little angle up here in the skinnier of the two triangles. Okay. So we know that two solutions can exist. So I'm going to go down here and let's say triangle 1. You know, A, B, and C. And alpha, beta, gamma. And triangle 2. A, B, C. Alpha, beta, gamma. So from the given information, both of our A's, our A is known to be 12 in both cases. Our B are known to be 31 in both cases. And our alpha is 20.5 in both cases. Okay. For triangle 1, that's the larger of the two, we found that beta was 64.8. And based on this analysis, the second beta is 115.2. Okay. We can find gamma in both cases by just subtracting from 180. So this gamma is 180 take away the sum of those two angles. So it'd be 85.3 or 94.7 degrees. We do the same thing here. 180 take away the sum of these two. Is 44. So 135.7, which is 44.3. So all we need to do here is just find the C value. So we're going to use a law of sines for this guy to find C, and then we're going to do a different law of sines here to find C. So for this one, you know, sine of 20.5 over 12 must equal sine of 94.7 over C. Cross multiply. And then divide. So C will be equal to 12 times the sine of 94.7 divided by the sine of 20.5. So C is 34.2 approximately. Okay. So there's our first one. For this guy, we're going to have to use a different angle because our C angle is different here. So sine of 20.5 over 12 equals sine of the new gamma angle is 44.3 over C. So C sine 20.5 equals 12 sine 44.3. So divide by the sine of 20.5. 12 sine 44.3 over sine 20.5 is 23.9. So now we have the solutions to both of our triangles, all right? So just to recap, this one's a little more intensive. You got to kind of think about this as two triangles. So doing this kind of graphical analysis is a good thing. So just keep in mind, watch out for what you're given, right? If you're given two sides and a corresponding angle, you need to be checking for one, none, or two solutions, okay?